Yeah, most of my videos, the way I record them, it's the mic automatically is in it. So, all right. First off, remember there is no class next week. Don't come. Enjoy your week off. Get your homework done. Get your project done. We will do the last part of it, the hypothesis testing, right when you get back. So you should have everything else done up to that point. Your graph should be done. Finding your mean, mode, median, population, whatever you're doing, the standard deviation, have that all stuff done. So this way, when we get back and I do that last hypothesis testing, it's just one thing you're going to be done and you're done with the project. So do definitely, when you're working on your data, come up with what you think is going to happen. That's what your hypothesis is. When we talk about the hypothesis testing after break, you'll figure out where to actually put the actual numbers, like the specific pieces in there. So, but believe it or not, that's a very small piece. Yep. Correct. No class next week. For mine, not everybody's. Oh, your English teacher's off too? How nice. All right. So today we're going to look at section 9.2 to be the end of chapter 9. Oh, I updated everybody's grades. I also, if your grade went down, I also put in the grades for the new homework. So technically, if you haven't done it, it's in there as a 0, but remember, 5 drop. So you can actually see your grade as of right now, even without doing any more homework. That's fine. No, I updated literally today. I pulled all the new data today. So if any homework that you did up till like 8 o'clock this morning is in there now, is in Blackboard. Yeah, the homework and everything else, all in Blackboard. So you can actually look at your grade and say, okay, if I don't do any more homework, what's my grade? And if I do homework, it's all your grade is just going to obviously go up from there. So, all right. So today we're going to look at estimating a population mean. So if you think back to what we did on Tuesday, we were trying to basically figure out the confidence interval for a proportion. All right. The goal is to find out, be confident in where the actual value is, given the information that we have. So if I'm going to do that for a mean, that means I don't have anything about the population. Okay, I don't have the population mean. I don't have the population standard deviation, which means my z-test that I've been using does not work. Because to do that, I need the population standard deviation and the population mean, because that's going to be in the middle. So we have to do something slightly different for it. And that's what we're going to look at. So first off, the point estimate for this one is my X bar. So this is now my point estimate. So X bar, just like P hat. And we're estimating the population mean. Okay. That's what we're trying to figure out. What's the actual mean of the population? All right. So there is a few things you have to do before you can actually, in reality, do these. You have to know that the data is normal. All right. We're 99% of the problems that you're going to do you're going to assume that it is normal. So we're going to make the assumption that this data is normal. This one is. It was done. So the first thing we need to do with this data is we need to find our mean and our standard deviation. Okay. So remember, I have those. We have to go back to some of the older calculators for this one. Standard deviation calculator. So we just put them in our standard deviation calculator. So 42.3 So I've got a mean of 41.55. And since this is a sample, I'm going to use the sample standard deviation is 3.51. Okay, so those are the two numbers that we need. You need the mean and the standard deviation. And this calculator is A2. A2. Standard deviation calculator. Yes, because remember, population and sample. This is a sample, so we use the sample. Okay, so we're using this one. So 41.55 and 3.51. That's my X bar. And 3.51 is my S, my standard deviation. Okay. So just a quick reminder of how to do that. All right. Any questions with those? Yes.
I'm sorry, what did you say the calculator was again?
A2.
A2.
A2. I don't know why. Wait. I take that back. It's A11. I don't know why it says A2 there. It's
Yeah, all
A11.
the appendixes are different on the.
Yeah.
They say like appendix A2, but it's A11 on the
Yeah,
other ones are like that too.
I'll have to fix that. It's because of when I made them compared to when I put them in here. So that's okay. I fixed that. Yes. X bar because it's a sample. It's the point estimate. So I don't. So this it is the mean, but it's not the population mean. No, this is sample mean. This is the sample. I don't have. That's not all of the data. No, population is the sample standard deviation. So that's why I used the sample side. It's got both. This is the population, this is a sample. Since this is a sample, I use the sample standard deviation. Mean is calculated the same no matter what. Yeah, the calculated is the same. But when you're doing standard deviation, the sample one is calculated slightly differently. So that's why we have to use the sample standard deviation. All right. So we now get to use this information to be able to determine our confidence interval and those type of things. But since we don't have, because if you remember the Z, I'll show you over here. We go back to 8. Remember, we're looking for that standard error. That is all population. Okay? I don't have a population. I don't know the population standard deviation. So I can't use Z to do it because I need the population standard deviation to do the Z table. So in this case, we're going to use what's known as the student's t distribution. And I learned something new today because apparently in the book it told you why it's called the student's t distribution. And I'm going to ask the people at Guinness Brewery when I go on Saturday, the actual Guinness Brewery over in Ireland, if this is true. We'll see if the tour guide really knows his math. The student's t distribution, basically, it allowed us to do the standard or the turn it into a normal curve, even if we don't know the actual standard deviation of the data. Now, since we don't know the standard deviation of the data, and we're typically dealing with smaller samples, it gets a little bit fuzzier. So I'm going to show you this. I have a nice graph for this one. So this is, that would be a nice bell curve, right? That's what we would have. Now, as my number goes down, you're going to start to see a dashed line forming. And until you get below 30, it's really hard to see. But let's say we're at 15. You can start to see that dashed line? And you see it down here too? That's the difference between that normal curve and the teacher and the student's T distribution. So as we get really small, you can start to see how it's really more dramatic. So the dashed one is my, I had it backwards. The dashed one is my normal. The purple one is my T distribution. So you can start to see it's a little bit higher on the tails. So it's close, but where you start to see the biggest difference is on those tails. Okay, so as you get further and further away from the center, that's when you start to see that difference forming. And if I had a sample size of 20, we're about 8% off on that two standard deviations. But if I go up to 30, now we're only about 5% off. What's the value that I consider unusual? 5%. So once you get over 30, the graph is actually pretty close to a z-table. And in a lot of situations, unless you need precise accuracy, you typically can go to a z-table after 30. I wouldn't do that in the homework because it'll be slightly off and they'll probably mark you wrong because it'll be off enough. So, and we get to like say 100, now we're at less than 2% difference. So it's not going to be that big of a difference in there. Okay. So that's where that t-table or the t distribution comes in. Few properties of it. We need to know what's known as the degrees of freedom. So the degrees of freedom is the value of n minus 1. So n is the sample size, and we subtract 1 from it. So in the problem that we just did here, we had 16 values, right? So my degree of freedom would be 15. So I'd move this over to 15. And that purple line would be my curve. So it's close, but not exactly what it is. All right, so you need your degrees of freedom, and you need the mean and the standard deviation. T distribution, just like the z, is centered at 0. It's symmetric. The area under the curve is always 1. The area under the curve to the right is the exact same as the area under the curve to the left. As t increases, it goes without bounds, so it's never going to equal 0, and it's never going to be 100%, just like the z-table. So those things are all very similar to your z distribution and the normal curve. Kind of showed you that. So you can see here they gave you a little bigger of a curve. They made it a little tighter. So you see the normal curve is the blue one, and a normal curve with 15 is closer to that, and 5 is a lot further down than that. So, and you really tell it, like I said, again, at the ends and directly in the middle is where you can see the biggest difference. Carolyn, you did the homework. How much? Can you just do it with the calculator that I have? Or do they need the? Okay, perfect. Then I don't need the table. Okay. I'm going to show you the table because actually I'm going to show you how it works. So the t-table, unlike the z-table where it has like, you're basically looking for the z, This one actually gives you the probability. Julia. For Brad. This one literally gives you the probability right in the table. But you just need to know what you're looking for and the degrees of freedom. So the problem that they're having you do here is my t-value is 10.1 and a 15 degrees of freedom. So we look here, we go over to t of 90, and we go down to 15 degrees of freedom, and that's my t-value. T-value, just like z, that's how many standard deviations I'm away from the mean. Okay, remember the z is telling you how far away from the mean I am? That's what this is telling me. That's telling me I'm 1.341 standard deviations away from the mean. And at that point, I could do all the other stuff that we didn't have to do because we have a calculator for it. But it's nice to know and see at least once. So on the z table, the 90 is 1.28. But if you look at the t table, the 90 is 1.341. So it's close, but not exact. So there you go, so 1.28. The other nice thing about the t table is down the bottom, here's your confidence level, and here's all your z-scores. 1.645, 1.960, 2.576, they're all right there. It's actually a very nice table to have. It is in the back of your book, and it is in on the online stuff too. So T just allows us to do it with smaller groups, and if I don't know the population. So, and honestly, it's instead of Z, yeah. So most times you're not going to have the population data, right? Because you're looking for new stuff. You're collecting the data. So you're not necessarily going to have the population data. So the T table is actually used a lot more often because of that rule, right? Because I don't know what's going on. If I already knew what was going on, I wouldn't have to do this. So we do use the T table a lot. All right, let's make our confidence intervals. Confidence intervals, same concept as we did with the population one or the proportion one. You have in the middle, you're going to have your mean, and we're going to add the standard error, and we're going to subtract the standard error. And that's going to give you your lower limit or your lower end, lower estimate, and your upper estimate. Okay? Same process, your confidence intervals, same concept. We're going to use 90, 95, 99. There might be some other ones in there. Okay? Same process, though, with those. Nothing drastically changes. Margin of error, you're not going to have to find. Normality. I'm telling you this because it's something you need to think about. But like I said, most of your data is either going to be normal or we can assume it's going to be normal. Most of the problems you're going to deal with. He assumed the data came from a population that is normally distributed. We would have to prove that typically if it's less than that. That's actually what Chapter 4 did a bunch of when we actually throw it into a graph and make sure it comes out to be as close to a linear line as possible. The more linear it is, the more normal it appears. You can also do it with your box and whisker plot. So we'll talk about specifically how to do this briefly when we do Chapter 4 at the end of the semester. But for these problems, you're just going to assume it's normal. All right, so let's go back to my wonderful car problem. My mean was 41.5. Was it 41.5 or 45.1? There you go. It was 351. And my 3.51. 351, right? Okay. This is where my quick little dyslexia comes out. I reverse numbers sometimes. All right, so we've got that, and we're looking for a 95% confidence interval. So we're going to go to this calculator. On the table, it is calculator A30. Let's see if it was actually called A30. It is. Okay, so A30 is right. So my mean, 41.55. My standard deviation, 3.51. My sample size was 16. And my confidence interval was 95. Since it is a small sample, this does come up and say you should check normality. We're going to assume it's normal. It is going to give you your standard error. The margin of error is just the difference between the two. So why is that different? Hold on a second. I'm going to do a calculation now. $15.95. 2131. Okay. Oh, 351. There we go. Okay. I'm going to get rid of that number there because you don't need the standard error. That actually is the standard error. I'm going to fix that. The 1.8703 is your standard error. That's actually the value that should be. I don't know why it says standard error and margin of error. I will fix that. Yes.
So for the t-value, you can either use the chart or the formula?
Yeah. So actually, no. Let me take that back. The formula uses a chart. You need the t. This formula right here.
No, for the formula for finding determining the t-value.
This.
Yeah, so that's the formula. We can use that, and we can also use the chart.
Yes. It depends on what you're looking for, though.
Okay.
Because if you look right here, what's that? What's the right? If I don't have it, I can't do this part. So this is the piece where you're looking at if you're going to figure out exactly what the t-value is, because I know the population standard or mean, I can figure that part out. But since most of the problems you're going to be doing in this section, you will not have that because we're trying to estimate that. And if I already knew it, I wouldn't have to do it. That's why we're going through and we're creating a confidence interval to figure out where that is. So you're going to look at the t-table given the information it gave you to find the value, and then you can use that to find the error. So, no problem. All right. So my error was 1.870. And then that's my confidence interval. So now, unlike the ones we did on Monday or Tuesday, sorry, those are not percentages. Those are means. So I am 95% confident that the mean miles per gallon of a 2019 Honda Accord is between 39.67 and 40.42. They used to. Let's see if they actually still do. They don't really. They used to actually put that on the sticker. So underneath fuel economy, it would actually have that range. It wouldn't just give you a single number. Okay. Because that number right there, even the city and the mileage, are estimates. Okay. And as with any estimate, you have a range. You do not have a single number. So odds are they're giving you that number. Okay, which means you could be anywhere down from 40 to up to 43, depending on how you drive, where you drive, and everything else. So, all right, I want to do another one of these. All right, let's look at this problem. Okay, so a botanist sampled 25 orchids with a mean height. So they gave me the mean is 32.5. And a standard deviation, so my sample standard deviation is 4.2. And I have an N of 25. So what's my degree of freedom? Degrees of freedom is always one less than the number. So my degrees of freedom in this case is 24. I want a 95% confidence interval. So show you on the table. So 95% confidence interval, 5%. And if we go down to 24, that's where that 2.064 comes from. But now let's use the calculator. So my, what was it, 32.5, standard deviation of 4.2, sample size of 25, confidence interval of 95. So my real mean, yeah.
So how does the confidence level corresponds to 0.05?
Yes. But, so if you look at the tables, you got to remember, if we're doing confidence interval, we're looking at both sides, right? So that's why I'm using this one here and not this one, because it's two tails. You're looking at both ends. The 5% split between the two ends. So if you're using the tables, that is something to keep in mind. Is that you want to use for confidence intervals, because we're looking at both tails, we're looking at both ends. It's a two-tailed. After break, we'll actually talk about hypothesis testing, where sometimes you only look at one tail, sometimes you're going to look at two. Sometimes you'll look at the left, sometimes you'll look at the right, and we'll be able to figure that stuff out from this too. So, and I'll explain what the one-tail stuff looks like.
Where is this table?
It-
The one on Pearson is not as.
Oh, I just typed in T-table to Google.
Oh, okay.
It's San Jose University is the one I use all the time. So it should be the first one that comes up on everybody's, honestly. It's probably the most accurate and easy to use. This is literally the table I used to print out for my class for their final because it has the T-table and it gives you the Z-scores on the bottom, so I didn't need to give you the Z-table. No problem. All right, confidence interval. If I change my confidence interval from 95% to 90%, what's going to happen to that confidence interval? Is it going to shrink or increase? Or is it going to shrink this way or get larger? Shrink. Remember, it's counterintuitive. It's the opposite of the way you would think. So yes, if I change this to 90%, oh, that's right. It gets smaller. If I go up, it gets larger. I need a bigger range to be more confident. Okay, good. All right. Now, this one is the formula is slightly different from this one than we did for the proportion. Determining sample size. You will notice they use Z in this formula, not T. Because when I'm looking for sample size, my numbers are typically going to be quite large, and T doesn't really matter at that point. So they will always use Z in this case. But it is still my sample mean or sample standard deviation. And in this case, E is not a percent. E is how far away from the mean I want to be. So if I wanted to find my sample with a 95% confidence interval, so I would use the 95% as 1.96. My standard deviation is 3.151. And I want to be within a half a mile per hour, or half a mile per gallon. Okay? Notice that's not 50%. It's the same unit as I'm talking about in this case, which is miles per gallon. So I want to be within 0.5 miles per gallon. Do that whole thing squared. So N in this case would be 189.3, which we always round up. So I need 190. So I would need to sample 190 cars to determine my miles per gallon within a half a mile per gallon. Which means that that error, so if we go back here, so if mine was 41.55 and my standard deviation was 3.51 and I had 190, my margin of error, 0.5023. So it's pretty close. So by having 190 in my sample size, that's another way you can shrink your confidence interval. Get more data. The more data you have, the smaller that confidence interval is going to be. Okay. Any questions? We're done. That's it. That's 9-2. The reason these lessons are going so quickly is because we've already covered all the stuff that you really need to do to it. It's just adding one extra thing to it. And even chapter 10, the beginning of chapter 10, when we start talking about hypothesis testing and stuff like that, and null hypothesis and alter hypothesis, that will be new. So it'll be a little longer, but once we do the calculations, it's going to be just as quick. So what do you have to do with your projects next week? Everything should be done except for the hypothesis testing, because that's the only thing I haven't shown you yet. Okay, and you'll have that the week after break. We'll have that covered, so you could actually start doing that for it. So, okay, all right. Have a wonderful week off. I will see you a week from Tuesday.